The Rehabilitation Report and associated soil studies were undertaken by Rob Locke of Landlock. Rob has over 30 years mine rehabilitation experience and is a contributing author to mining industry best practice documents and reports. Landlock's technical review of rehabilitation identified a range of options and methods to be considered in the context of rehabilitation goals and the current state of rehabilitation knowledge. Rehabilitation goals. What stakeholders want? What is achievable and where? What constitutes rehabilitation success? Which aspects of rehabilitation are most critical for success? How to achieve those goals? Reliably, sustainably, cost-effectively. What areas of uncertainty still remain requiring research, trials, or more data? It informs mine planning on what materials may be needed to support rehabilitation's works so that required materials are available when and where they are needed, how materials are to be placed. It also provides the technical basis for development of a mine rehabilitation and closure plan. The advice and options in the technical are not final. With time, experience from carrying out works and greater information on material properties, the influence of climate and stakeholder aspirations will quite properly result in some variations to the initial planning. Rehabilitation planning, if done properly, integrates a lot of information. The existing environment, climate, landscapes, soils, vegetation, land use provides a lot of guidance. Setting goals is critical. Rehabilitation should be a very targeted activity. Mining and processing methods can greatly impact on rehabilitation plans and works as they affect what materials may be available for rehabilitation works and when, and the types of landforms that will be created. Soils and soil management are critical to providing a suitable growth medium, and rehabilitation is much more successful and reliable when working with good quality growth media. Also important is the identification of what specific rehabilitation practices may be best suited to the particular project. The range of options for landform construction and shaping, soil placement, final surface treatment, fertiliser rates, formulations and placement, amendments and surface stabilisation treatments is simply enormous, and these should be tailored to the site and its specific risks and requirements. Components of the existing landform considered in detail include landform which for the Fingerboards project can be described as a dissected plateau. Climate, with particular emphasis on rainfall and temperatures which affect plant growth, soil productivity, runoff and erosion. Soils, which in this area are largely of low productivity with significant limitations to plant growth and some potential for instability. Vegetation, which affects stability and function and is largely governed by land use. Land use, which in the area is largely grazing, though with a significant area of forestry and some remnant vegetation. Function. Is the current landscape functional? Generally, landscapes that retain water and nutrients are considered more functional than landscapes that shed water and nutrients relatively quickly. There is also the important question of what aspects of the current landscape appear to be critical to its function and stability. It can be inferred that, overall, the area, due to some clearing of trees and heavy grazing, would have elevated rates of surface runoff and of seepage of infiltrating rain to depth relative to similar land in pristine condition. The existing landform has distinct zones associated with runoff movement. Runoff on the flat plateau top moves into broad swales which concentrate runoff from the plateau top and discharge it into the valley side slopes, which also carry less concentrated flows in places. Runoff finally moves into the flow channels and becomes part of larger, deeper flows that leave the area. Seepages of infiltrated rain that moved to depth in the plateau may exit on the channel side slopes and contribute some small risk of tunnel erosion. Risks of erosion are highest where flows are concentrated and where gradients are steep. Achieving erosional stability is a major priority for those high-risk areas. Minimisation of seepage is a priority for all areas bordering the plateau top, indicating that some increased density of trees would be desirable in those areas to dry the soil to greater depth. In contrast, as the largest area and as the major source of runoff, the water balance on the plateau top is quite important. Increasing the amounts of water that can be stored in the subsoil will increase annual water use by plants, giving more resilient vegetation and more productive pasture. It will also reduce deep drainage and seepage exiting valley slopes. However, even with changes in the soil and increased plant growth, runoff is only likely to be reduced in smaller rainfall events. Although records show similar average rain in each month of the year, variation in potential evaporation means that there is, on average, a pronounced winter wet season, when rain exceeds evaporation, and a definite summer dry season, when evaporation greatly exceeds rainfall. As plant growth is least during cold conditions, the winter period, although wet, is not likely to provide the bulk of plant growth. Rather, plant growth will be highest in autumn and spring when temperatures are higher and evaporation is not as great as in December and January. As there will, on average, be a shortage of water for plants in both spring and summer, plant growth will also depend on the amount of stored soil moisture that the plants can use. Consequently, soils able to store larger quantities of water will be more productive and plant growth will be less susceptible to dry periods. The wet winter period, when soils may be saturated for significant periods, will generate significant drainage to depth, particularly in soils that are highly permeable and have low capacity to store water. Given concerns with respect to tunnel erosion, high rates of deep drainage are not desirable. Soils in the project area fall into two groups in the Australian soil classification. The first is podosols, which are deep leached sands, often with gravel at depth. There is also a shallow podosol, with gravel at relatively shallow depths. These soils have low chemical fertility and low water holding capacity. Infiltrating water passes rapidly through these soils and moves to greater depth. The other soil type is sodosols. These are duplex soils, so called because they have two distinct layers, a surface layer called an A horizon of sandy soil, overlying a layer called the B horizon, much higher in clay that is quite unstable due to elevated levels of sodium and magnesium. The B horizon is very dense, very hard, of very low permeability, and penetration by plant roots is very limited. Because the B horizon is impermeable, under heavy rain the A horizon can saturate and low runoff rates can then become quite high. If exposed on the surface or exposed to the subsurface seepage flows, the B horizon is highly erodible. Across the project area, the surface horizons of these two soil types have very similar properties, with the distinguishing difference being their B horizons. Both major soil types have limitations of low chemical fertility, as the sandy surface layers, the A horizons, have low capacity to retain or accumulate nutrients. Similarly, the subsoils of either soil type are of limited value for plant growth. The sandy podosols retain little water or nutrient, and the hard-setting B horizons of the sodosols are unavailable for plant roots. The obvious option to improve soil productivity in rehabilitated areas is to amend where necessary with lime or gypsum to improve soil physical properties and apply a range of fertilisers to improve chemical fertility. However, an equally important and more lasting improvement in soil properties can be achieved if the current subsoils are replaced with a soil material that is well structured, permeable and not hard-setting, but has significantly greater capacity to store water. The ideal subsoil, particularly for areas where erosion risk is not high, will have higher clay than the podosol subsoils, but will not have the structural problems of the sodosol subsoil. For pasture and grasslands in particular, such a soil would achieve both increased grass and legume growth and reduced deep drainage. Increased vegetation growth may reduce runoff in some smaller events, but the overall impact on runoff of a changed subsoil can be expected to be small in larger rainfall and runoff events. Overburden is the material overlying the mineral sand, effectively the layer between the deposit and the surface soil. It is composed largely of two layers of the Haunted Hills Formation, which is a fluvial deposit of sands, clays and gravels. Layers in the project area are classed as clay or gravel, depending on the amount of gravel present. The overburden has low to moderate salinity and no potential for acid mine drainage to develop. However, it does have elevated levels of sodium and magnesium, which means it can be unstable on wetting, of low permeability, and potentially hard setting. The processing stream produces quantities of sand tailings and fine tailings. Neither of these are saline, and the sand tailings is effectively chemically inert. The fine tailings has an elevated level of sodium, but low levels of arsenic and other trace metals. Neither the fine tailings nor the sand tailings are radioactive. Approximately 90% of land in the study area is classified as modified and disturbed. This includes a timber plantation in the western section of the project area. Native vegetation is concentrated around roads and the various gullies. Land use is predominantly grazing, with significant clearing of trees having been carried out and a range of exotic grass and legume species introduced. High levels of grass cover are important not only because grass increases rates of infiltration of rainfall, but also because grass is extremely effective in spreading overland flows and preventing erosion. Relative to conditions prior to European settlement, the current grazing land use and associated clearing of native vegetation can be expected to have resulted in increased rates of surface runoff, increased rates of drainage to depth, and reduced water use by vegetation. Deep-rooted tree vegetation is able to extract water from greater depths and is able to transpire water more consistently through all seasons of the year. Consequently, by increasing tree cover in areas bordering the plateau top, seepage onto valley slopes can be reduced and stability of the steeper slopes increased. Re-establishment of grazing land, effectively an open woodland, is planned for over 50% of the total area. Priorities are to maximise surface cover and achieve pasture productivity equivalent to or better than pre-mining condition by improving soil chemical and physical fertility. The western part of the project area is planned to be returned to native grass woodland, which will be managed as a native vegetation conservation area with priority to maintain surface cover and promote biodiversity. Other key areas are swales, valley slopes, and channels. Control of erosion is important for these areas, and grazing is planned to either be initially excluded or limited for swales and excluded for valley slopes and channels. Tree densities in steeper areas are planned to be higher to minimise seepage, with riparian vegetation to be established along drainage channels. Rehabilitation goals for fingerboards are that the lands are safe, stable, non-polluting and productive over the long term. This would mean the landforms, soils and hydrology of the site support sustainable farming land uses and ecosystem functions. The capability of the land to support commercial, ecological or cultural uses should be similar to or better than the land prior to mining. For native vegetation domains, this means restoring species or establishing functionally rich vegetation communities. Broadly speaking, rehabilitation strategies will focus on improving and managing soils, sourcing and propagating native seed, in particular focusing on establishing native seed crops, optimising planting and seeding techniques, developing rehabilitation skills and capacities such as project suppliers and personnel, and monitoring and reporting on rehab outcomes. Topography of the project area after mining will be integrated with existing land surfaces and contours. It will be similar to the existing topography, with the exception of Perry Gully and the Honeysuckle Creek Valley. The upper reach of Perry Gully will be backfilled to form a broad plateau draining to the north and south, and also partly to the shortened Perry Gully. The Honeysuckle Creek Valley will be broadened. Final surface elevations of part of the rehabilitated surfaces, especially around the central plateau area, will be higher than the pre-mining surface. This is sufficient to accommodate any increase in the volume of backfilled material without affecting gradients in key, steeper areas. The relatively small change in overall elevations is expected because mineral sands mines have a much lower level of swell than do hard rock mines, as the excavated material is almost entirely alluvial. Erosion potential of landforms was assessed by calculating the LS, combined slope length and gradient factor, for the universal soil loss equation. Those calculations showed no increases in LS factor and therefore no increase in erosion potential across the steeper sections of the landform relative to the initial undisturbed landform. Erosion by rainfall and overland flows is sensitive to vegetation cover and slope gradients. Consequently, a major priority for rehabilitation is to increase, or at the very least maintain, current levels of surface vegetative cover. Higher soil fertility is obviously important in this, as it will increase plant growth, which will increase surface cover and reduce erosion. Increased grass cover will also reduce runoff rates in smaller events in particular, also reducing overall erosion risk. Reduction or elimination of grazing in some zones will be used to help increase vegetation cover. As well, the landform is planned to ensure that there are no steep areas of increased gradient relative to the existing landform. A further possible issue is for the concentration of flows as they discharge from the plateau top to the valley slopes and the flow channels. This will be managed by ensuring that swales located around the perimeter of the plateau top are formed at a similar spacing to those currently present, and that all have broad U-shaped cross-sections similar to the more stable swales currently present. Potential for subsurface tunnel erosion will be addressed firstly by ensuring that there are no areas of prolonged ponding on the final landform, as ponding and deep infiltration at a point is a key driver for tunnel erosion. As well, care will be taken to ensure that subsoil layers possibly exposed to seepage movements are amended with gypsum and stable. Tree placement will also be planned to minimise deep drainage and seepage flows, as deep-rooted vegetation will dry soil to greater depth. Tests of soil profile reconstruction were carried out to compare a range of options for constructing more functional subsoils in rehabilitated soils. The aim of these studies was not to provide an exact prescription for soil profile reconstruction, but to identify options that clearly would not be useful and to point towards promising approaches that could be further trialled and refined. Testing used 200mm diameter cores, 1 metre deep, to compare subsoil, amendment and fertiliser options. All treatments had the same surface layer of topsoil. Some treatments have shown excellent plant growth. A range of subsoil options were trialled, including mixes of coarse and fine tailings, 2 overburdens, and a range of added amendments and fertilisers. A wide range of measurements were made to help identify which options were most likely to be successful and productive. Permeability is of concern, as an impermeable subsoil will cause waterlogging and little water will enter it. Water holding capacity varies enormously and, as shown on the slide for growth under water stress, can greatly affect plant growth. Responses to fertiliser and amendment were significant, and analysis of the soil following the studies have pointed to potential improvements in fertiliser practice. This cross-section of the planned rehabilitated landform shows a number of attributes of the conceptual profile as currently planned. Please note that this cross-section has vertical exaggeration of a factor of 5. Firstly, the dashed line showing original topography shows, for this transect, an increase in the elevation of the reconstructed landform in the middle section of the plateau, and how that landform is tied into the existing topography at the margins of the plateau. This section shows placement of gravelly material under the planned road alignment to ensure geotechnical stability of the road. It shows differing placement of overburden and fine tailings at depth, overlain by a soil profile of at least 1 metre depth. It also shows purposeful placement of more gravelly material underlying the steeper slope sections, so that rehabilitation works will develop a more rocky and erosion-resistant surface. It also highlights the planned increasing density of trees at the plateau margin and in the area of the flow lines. This slide shows the typical progression of mining across the landscape. The sequence commences, on the far right of the slide, with topsoil being conditioned, having fertiliser and amendments such as lime and possibly compost being applied at rates determined by soil chemical analysis. Then the topsoil is stripped, with the stripping process thoroughly and reliably mixing amendment and fertiliser throughout the soil. After the third year of mining, the topsoil is then directly transferred to an area marked topsoil replacement, prepared for rehabilitation and spread. This direct transfer minimises any loss of organic matter and soil microbes. After the topsoil is stripped, there is then a sequence of overburden removal, mineral sands recovery, followed by replacement of tailings and overburden and placement of a replacement subsoil. The topsoil is then replaced and revegetation works are carried out. A key aspect of this is that revegetation works are part of a continuous process. The areas to be rehabilitated each year are not large compared to many mining projects, and there is opportunity for continuous learning and improvement. These slides show the gradual progression of mining and rehabilitation across the project area. They highlight that as mining nears completion, the great majority of mined area should have been rehabilitated. Planned rehabilitation for the Fingerboards project has a number of key aspects that align with best practice in mine rehabilitation. The first is that rehabilitation occurs progressively. This is considered the optimum way for mines to be rehabilitated and ensures constant feedback and improvement and the development and retention of skilled rehabilitation practitioners as part of the mine workforce. The ability to rebuild soil profiles from the bottom up can deliver designed profiles tailored to site conditions and rehabilitation goals, and enables a degree of amendment and fertilisation that is unusual in mining practice. Direct transfer of topsoil is considered best practice for the preservation of soil microbes and organic matter. Adding fertiliser and amendment to topsoil prior to stripping is commonly recommended, but seldom done in practice. It ensures the highest possible soil quality for vegetation establishment and growth. Ongoing analysis to characterise wastes and soils is key to ensuring that soil management is optimised. Monitoring is a critical component of rehabilitation programs. Rehabilitation that fails is the most costly rehabilitation that can be done. Consequently, it is in the mining company's best interest to be sure that their rehabilitation works are successful, and if not, to quickly find out why and then change methods. But bear in mind that Mother Nature is not always a nice lady, and even the best rehabilitation works will sometimes fail or do poorly if climatic conditions are poor. Rehabilitation monitoring typically has short and long-term components. In the early stages, monitoring typically focuses on vegetation establishment, both plant numbers and species, and erosion control. If intervention or repair is required, those works should be carried out promptly. Similarly, if rehabilitation practices used do not appear to have been entirely satisfactory, then modifications would be made. As vegetation cover levels increase, there will be greater focus on species presence, diversity, weeds and pests, and on productivity in pasture areas. At longer time periods, focus is likely to shift to consider ecosystem sustainability and achievement of target soil profile properties such as carbon and nutrient stores. There is enormous experience with the revegetation of disturbed land on agricultural, construction and mining areas. Specific methods to be applied in the rehabilitation of the Fingerboards project will evolve, but will also need to be modified on the basis of climatic conditions. In general, seeding will be used for grasses, legumes and forbs. High seeding rates will help to compete with weeds. Some seeding may be used to establish trees and shrubs, though it is likely that use of tube stock will be common. A range of methods for protecting small trees and shrubs from grazing are available and likely to be necessary. Where risk of erosion by water or wind is high, or where germination and establishment may be difficult due to climatic variability, hydroseeding or hydromulching may be needed. Glues used with such applications can greatly increase soil resistance to erosion, and the mulch cover can help to retain soil moisture and increase plant establishment. Challenges that will be addressed in revegetation works to agricultural domains would include the management and improvement of post-mine soils to reduce erosion potential, increase plant available water, improve soil fertility and structure, restrict weed growth and manage overgrazing by herbivores. This slide shows an area of about 150 hectares of restored pasture land 3 years after completion of rehabilitation works at the former Waroona mineral sands mine in Western Australia. This image is from 2015. Weeman Mineral Sands Mine, approximately 80 kilometres southeast of Mildura in Victoria, operated between February 2001 and January 2004. The land, formerly used for mining of mineral sands, has been transferred to a private landowner and is now used successfully for vegetable production. For revegetation works in native-focused domains, the aim will be to establish a broad range of native species that are representative of locally defined ecological vegetation classes. In practice, this will mean aiming to increase the extent of open native grassy woodland. There are several examples at various locations in southeastern Australia of successful smaller-scale direct seeded restorations of complex native grassy woodland. Creating complex communities and habitat niches has been shown to create opportunities for faunal colonisation. While the use of native wildflowers and grasses on road verges can increase visual amenity and reduce roadside vegetation management requirements. Some of the challenges to be addressed in native restoration will include ensuring there is a source of seed from a broad range of native species, which will be done through seed production techniques, and ensuring that there is the restoration infrastructure and capacity to undertake restoration and manage restored landscapes. This image shows an extremely successful example of native grassland restoration on agricultural lands. Compared to typical mining projects, changes to the existing landform are not large and do not create unnatural or dysfunctional landforms. Existing land uses will be retained over much of the area, with such changes as are planned aim to improve landscape stability and function. Off-site impacts should be minimal. A distinctive aspect of the rehabilitation planning for this project is its integration of landform, soils, vegetation and land use to achieve a functional landscape. Rehabilitation works will focus on improving soil physical properties and enhancing chemical fertility to increase the reliability of rehabilitation works and to maintain or increase the productivity of grazing land. The materials excavated are benign. There are no issues of salinity, acid mine drainage, or radioactivity to be managed. There are a number of potential benefits to a successful Fingerboards rehabilitation program. These would include the reinstatement of productive grazing pastures, increasing the extent and range of threatened native vegetation communities in the Gippsland region, increasing the extent and quality of habitat for native fauna, increasing local amenity and recreational opportunity for local communities, developing important seed and restoration infrastructure for long-term use in the local area, providing opportunities for engagement and for training and education with local communities, schools, businesses and interest groups in restoration-related activities, and providing opportunities for engagement with Indigenous groups, for example skills transfer and promotion of cultural knowledge.